Now we're going to animate our pieces so it looks like they're actually falling down from the top of the board instead of just appearing instantly. To do this, we'll need to change our fill function to be a coroutine. A coroutine is a function that can execute across multiple frames versus a regular function which has to execute in one frame. Open up the grid script. We first change the return type of our fill function to be IEnumerator, which means it's a coroutine. We also need to change how we call fill, since coroutines must be started with start coroutine. Next, we're going to add a new parameter called fill time, which is the time between calls to fill step. A lower fill time means the board will fill faster, while a higher fill time means it fills slower. Now we just wait that many seconds in between calls to fill step. That way, our fill will happen gradually over time. We can do that using yield return new wait for seconds. Hit save and go to the editor. Click on the grid object in the scene and set fill time to something small, say 0.1, and go ahead and hit play. You can see as each row of the board is filled, but this still looks a little choppy. Each piece needs to animate as it moves from space to space. To do that, we'll change move in the movable piece script to also be a coroutine. To start, we're going to create a new variable to store a reference to our move coroutine. First, we'll add a function to store our move coroutine. This way we can stop the coroutine if we get another move command before we finished animating. The move function now just becomes a wrapper that starts and stops the coroutine. If our stored coroutine is not null, go ahead and stop it using stop coroutine. Then we get a reference to a new coroutine. I'm using a function called move coroutine, which I'll define in a minute. The last thing we need is how long the animation should take. Add a new parameter to the move function, which is a float telling us how many seconds the animation should play for. We'll also pass the parameter to our move coroutine that we're going to write in a bit. Head back to the grid script and update all the calls to move to pass in a time. In this case, we're going to use our fill time, so that the time it takes the board to refill is the same amount of time it takes a piece to move from one space to the next. Now we'll write the move coroutine. Again, this will return an IEnumerator, and the signature is the same as our move function. The move coroutine is going to interpolate between the starting and ending positions for the piece, moving it a tiny bit each frame. Our starting position is simply our transform's current position, and we can get the ending position using the grid's getWorldPosition function with new x and new y. Next, we're going to interpolate between start pause and end pause. Interpolation is getting a value in between two other values based on a parameter which we'll call t. For example, if t is 0, then the interpolation would return the starting position. If t is 1, it would return the end position. And if t was 1/2, it would return something in between start pause and end pause. We're going to loop over values of t from 0 to however long our animation should take, incrementing t by time.delta time each frame. Time.delta time is the amount of time the last frame took. The reason we're looping t from 0 to time instead of from 0 to 1 is because this way our animation will take exactly time seconds to execute. We then set the position of the piece to our current interpolation. We divide t by time to get a value between 0 and 1. And yield return 0 just waits for one frame. At the end of the loop, we'll set the position of the piece to our ending position, just in case our loop didn't get all the way to end pause. That takes care of our animation, so now we just need to set our x and y parameters to new x and new y. Go ahead and hit play, and you can see that all the pieces nicely animate in. However, if you look at the object hierarchy, you might notice a problem. There are tons of empty pieces even though the board is filled. This is because we're not cleaning up the empty pieces before moving the new piece into it. This is why it's so important to clean up objects when you're done with them. Luckily, this is easy to do in Unity using the destroy function. In the grid class, we'll simply destroy the empty piece below before moving a new piece into it. Remember that we're storing the game piece component of each piece, so to destroy the whole object, we need to call destroy on the piece's game object. Now when we look in the hierarchy, all the empty pieces are gone once the board is filled. Now that our grid is done, we can have some more fun with our game pieces. Next, we're going to be creating an obstacle game piece. We're now going to create a special type of piece that doesn't move. This piece is an obstacle that our normal pieces will have to fill around. First, we need to create a new prefab, just like we did for the empty piece. Drag the normal piece prefab into the scene from the prefabs folder. Select Game Object, Break Prefab Instance, and rename it to Bubble Piece Prefab. Remove the movable and color components in the inspector. Open the prefab, click on the piece game object, and replace the sprite with Bubble01. Drag the Bubble Piece Prefab object into the prefabs folder to create a prefab out of it, and then delete it from the scene. Open the grid script and add the new bubble piece type to our enum. Save that and go back to the editor and click on the grid object. Change the size of the piece prefabs array to 3. Set the type of the last element to bubble and drag the bubble piece prefab from the prefabs folder into the prefab variable. To test out our bubble piece, we'll create one in the center of the grid in the grid start function. First, we'll destroy the empty piece at the center of the grid, and then spawn a new bubble piece there. Go back to the editor and hit play. You can see that the pieces get stopped by the obstacle. Right now, no pieces can go below the bubble, but in the next video, we'll see how to fill the space below the obstacle. In addition to moving straight down to fill a space, pieces can also move diagonally. This lets pieces fill in under obstacles. We're going to update the fill step function to also move pieces diagonally. In the grid script, we're going to add a new private boolean called inverse. If pieces can fill diagonally, it means there may be more than one piece that could potentially fill an empty space. Since we don't always want the diagonal piece to come from the same direction, we'll swap the direction we're traversing the grid in every step and keep track of which way we're going using inverse. Now we just swap inverse after every call to fill step. Next, we'll update our loop in fill step so that we can change a direction of traversal depending on the value of inverse. I'm changing x to loop x. We'll use this value to calculate the actual x coordinate of our piece. If we're not inverted, x is simply equal to loop x. If we are inverted, then x is equal to the x dimensions minus 1 minus loop x. Essentially, when we're not inverted, we're traversing from 0 to the x dimension, and when we are inverted, we're traversing from the x dimension down to 0. Here's our code for moving straight down into an empty space. If we can move straight down, we're not going to bother checking if we can move diagonally. So our code for moving diagonally is going to go in an else statement if the code for moving straight down fails. I'm going to copy the code for moving diagonally from the code snippets file, and then we'll go over it. What we're doing here is looping through our two diagonals, down left and down right. If the value of diag is 0, this means it's the piece directly below us, which we already checked for up here, so we don't have to worry about it. Diag x is the x coordinate of our diagonal piece. Depending on the value of diag, this will be either to the left or the right of our current piece. For example, when diag is -1, this piece will be to our left, and when it's 1, it will be to our right. If we're inverted, then it will be the opposite. We check if the x coordinate of the diagonal is within the bounds of our board, and if it is, we get a reference to the diagonal piece, which is at y plus 1, the row below us. Now, we obviously can't move into a piece if it's not empty, so we check to make sure that the diagonal piece is empty. Next, we need to look at the pieces above the diagonal piece. The reason for this is, if there's another piece above the empty diagonal space, it can just move straight down to fill the space. We don't want to move diagonally unless there's no pieces above the empty space that can fill it. We loop through all the pieces above the diagonal space. If we encounter a movable piece, we break out of the loop, since this piece can simply fall down and fill the space. If we encounter a piece that's not movable and that's not empty, for example an obstacle, it means that this empty space is blocked and won't be able to be filled from above. If the piece can't be filled from above, then we'll fill it diagonally, and the code for this is the same as the code that we used to fill from the top down. Now when we run the game, the pieces fill in below the bubble. Try adding some more bubbles to see how the pieces fill in below them. I have code to create some bubbles in the code snippets. You can use this or just put them wherever you like. I'm placing this in start where we initially created the single bubble. And I'm just creating lots of bubbles in the 4th row as well as one in the top row. And as you can see, the pieces fill around all the bubbles. There are a few empty spaces that can't be filled even with diagonal filling. These will remain empty until we get to clearing the bubbles, which will be in a later video. Now that our grid is all set up, we're ready to start matching and clearing pieces. Now that we can fill our board with pieces, we need to be able to match and clear them. A player clears a piece by swapping it with an adjacent piece to match 3 or more pieces of the same color. They swap a piece by clicking and dragging from one piece to another. To detect mouse clicks, we need to add a collider to our game piece. Drag the normal piece prefab into the scene. From the component menu, select Physics 2D, Box Collider. This box collider will allow us to detect mouse clicks on the piece. The collider is represented by this green box. Since our sprites are anchored to the top left corner, we'll need to offset it, setting the X offset to 0.5 in the inspector and the Y offset to -0.5 aligns the collider with our sprite. In the inspector, hit Apply to apply this to all of our prefabs. And then go ahead and delete the object from the scene. Open the game piece script, and we're going to add some functions to detect mouse clicks. These functions are onMouseDown, onMouseEnter, and onMouseUp. We'll just stub them out for now. As the name suggests, onMouseDown is called when the mouse is pressed inside an element. OnMouseUp is called when the mouse is released, and onMouseEnter is called when the mouse enters an element. Open the grid script. The first thing we need to swap 2 pieces is to know if they're adjacent. Create a new function called isAdjacent, which takes 2 game pieces and returns a boolean. 2 pieces are adjacent if their row is the same and they're in adjacent columns, or if their column is the same and they're in adjacent rows. This returns true if piece 1 and piece 2 have the same x coordinate and their y coordinates are within one space of each other. Next we'll do the same thing, but if the y coordinates are equal and the x coordinates are within one space of each other. We also need a function to swap the 2 pieces if they're adjacent. Create a new function called SwapPieces that takes 2 game piece objects. We'll only swap the pieces if they're both movable. If they are, then we assign them to each other's positions in our pieces array. We then move the pieces from one space in the grid to the other. We'll store the x and y coordinates of piece 1 in these temporary variables so that they don't get overridden when we move the piece. We move piece 1 to piece 2's position and piece 2 to piece 1's position that we stored earlier. And that's it for the SwapPieces function. Now we just need to trigger it when the mouse is pressed. We need to know what piece we've clicked on and what piece we let go of the mouse on. Create 2 new private variables to store these pieces. One is the piece that we pressed down on, while the other is the last piece that our mouse entered the bounding box of. Now we'll assign these variables when someone clicks on the mouse or moves the mouse over a piece. Create 2 public functions, one for when we press on a piece and one for when we enter a piece. These will pass in the game piece that was clicked on or the mouse was hovered over. Later we'll have our game piece call these functions. In press piece we set our pressed piece variable, and in enter piece we set the entered piece variable. So we know the piece that the player pressed on, and we know the piece that they're hovering over. All that's left is to do the swap when they release the mouse. Add one more function for when they release the mouse. Here's where our isAdjacent function gets put to use. We check if the pressed piece and the piece that we were hovering over are adjacent to one another, and if they are, we swap them. Now we just need to trigger these functions from our mouse events in game piece. This is a reference to this game piece component, which is the game piece that we clicked on or hovered over. Go to the editor and try swapping some pieces around. As you can see, you can swap any 2 adjacent pieces. Next, we'll make it so that you can only swap pieces if they create a match.